Hello, my name is Michael Ljungberg. I'm a professor at the Medical Radiation Physics in Lund, Sweden, and also the developer of SIMIND code since actually 35 years ago. So in this webinar, I will let you know a little bit about some parts of the code that could be very useful for you to know about. As you probably know, the SIMIND code is available from a website that we have in Lund. So here is an address, and there is also a manual, which I cannot go into the details, but many of these examples has been described in the manual, and also the data files for the SIMIND are available as tutorials. The thing I want to go through is basically first to how to set up a voxel-based simulation, because this is what we will do in the examples. I will use the Zubal phantom and a Zub table that is included in the distribution. I want you also to understand the units of the images and the spectrum in order to work with these. I will describe how to set up a proper acceptance angle, which is essential and also can be some kind of error, source of error if you don't do this properly. I will talk about the scatter order and how to select that. I will talk about how to add noise to the images. And also I will show an example how you actually from the Zubal phantom, which is a normal distribution, can add tumors to that phantom or any other voxel-based phantom that you have. So the Zubal phantom is actually a created phantom, code-defined phantom that has been developed from a CT study where 58 organs have been segmented and given a unique code. So it is not just a phantom that you can use directly. In fact, you have to change those values that is code-based into activity distribution and density distribution, which is easily done in SIMIND by a table that you have to connect to this Zubal phantom. So in this table example, for example, the liver has all the voxels that belongs to the liver has a code of 12, and you can assign an activity value of, for example, 30, some kind of relative value of the activity concentration. There is also available a head phantom, which is created by MRI, and there is 62 structures in these. This has been developed by the group at Yale University in USA, United States, by George Zubal. That's why it's called the Zubal phantom. And the command that I will use is shown here, and this file here is actually this table that is used for the simulation. In this case, it's mimic a bone scan, whole body, and you can see this image here, and this is what we will run now. And you can find these files in the tutorial folders of the SIMIND distribution. So let us start simulate a whole body study and have something to work with. Now I have opened a terminal window where we will do the simulations, and I have typed the command for the simulation now, SIMIND MDP whole body, and you have see here that I have added a flag FA11, which means that I turn off the interactions in the phantom is just for speeding up the procedure a little bit. So now I run this, And it goes quite fast, and now the simulation is finished. And if we look at the folder contents, we will see that we now have a file called mdp_vb.bin, binary image. And now we have simulated that, and now we will look with this in the with a program called ImageJ. So now this program appears here, ImageJ, and I can now go in and import this file as a raw file. I select the simulated result file here, the BIM file, and you see that we now need to change this to 384 and 124. It's one image and it's in real float format, 32 bits. So now we have our simulation here. So this is according to the information in the Zubal file, and this is a whole body phantom of the Zubal. So now we have one image, and there is no interaction and scatter in the phantom, but you can see the whole distribution, including some activity in the kidneys. Sometimes you want to add tumors to the simulation or the phantom, and this can be done in a quite convenient way without going in and edit the phantom. So let us see how we can do this. So now we want to add 3 tumors to this phantom and on different places. So we can edit a file that the content shows the location and sizes of the tumor. The format of this file looks like this. It's 1 tumor per row. There is 8 values that I will talk about. The first 3 values here is the radius of the tumor in pixel units. Next 3 values is the actual location for the midpoint of the tumors in the Zubal phantom, also in pixel units. So this is the location in pixel units, and the K direction here is the direction along the patient. So it's this direction here. The next 2 values is the activity distribution, actually the same value as you define in the Zubal table. You also can, if you want, specify a different density for the tumor. If it's 0, then it doesn't change the initial value of those voxel locations. Let us go back to the simulation. I have this file here as a file called mdp vb input. So here are now these 3 values. I can provide this file to the SIMIND, and the SIMIND will go in and look for these locations and replace the values in the initial Zubal phantom voxels values with these values. The command now for this is just to add a switch called if for the input file and the name of the file. So now we run with 3 tumors. So let us now see how this looks in ImageJ. I didn't change the file name, so we will go in and open the same file name here. So now we have here 2 versions, one without tumors and one with tumors. So this is one way of adding diseases to this phantom. The next thing I want to talk about is the 2 collimators that is included in SIMIND code. The first one is an analytical collimator, and that is usually defined by index 53 in the CHANGE program. It's based on a Gaussian shape collimator response. So it's a purely mathematical collimator, and you cannot simulate any interaction in the collimator. So this is used, for example, with technetium or radionuclides that you know don't have any penetration effects. The other one is a more detailed Monte Carlo simulations of radiation transport through the collimator. It's a ray tracing collimator, and you access by setting index 53 to 1. In order to use this correctly, we need also to know a little bit about how the photons are exiting from the phantoms. They are not simulated isotropically, but rather they are forced to go into a certain cone. It's used to improve the speed. All exiting photons from the phantoms are not isotropic emitted, but they are emitted within a solid angle here, defined by an angle theta max. And this is controlled by index 19 in CHANGE. You can select different values from of this value, index 19. One value is then number 2, which actually calculate the acceptance angle from the properties of the collimator, hole length and the hole width, and then it calculates the most optimal angle. If you have collimator 2, which allow for penetration, obviously you will miss the penetration if you use this very narrow angle. So now you can let SIMIND calculate optimal angle for you, and that is given by the number 3. So now SIMIND looks for the distances between the source and the camera width, and it calculates an optimal angle that ensures that wherever the source is, it will be able to expose the whole camera. And there is also a possibility to specify a specific angle by giving a negative number to index 90. So for example, if we give number index 19 a value of -10, it will force the photons within an acceptance angle of 10 degrees. If we give it a value of 45, regarding of the size of the camera, it will emit the photons in a 45 angle degrees. And if we give a -70, it will broader up the angle. So now we will simulate a point source in air and to see these effects with the different collimators. I now write the command SIMIND point, which is a file defining a point source. And I turn off the scatter also here. This is now for technetium, 140 kV here. So let us now go in and look in image J. I select point here. I have changed to 128, 128 here. And we get a point here, point. If we now simulate the same thing, but we change the initial angle to number 3, which means that we expose the whole camera. We get a new simulation here, and we go in and select point again. We don't see any difference here. And that is because we are using the analytical collimator. So we can now, we use collimator 53 equal to 1. So we run that. Takes a little longer time to run this because there is more steps going through tracing the photons in the lead. File again, raw, point, and we see no difference at all compared to the other. So why is that? Well, that is because we are simulating with technetium, and that has very little penetration. So if we now define a photon of 400 keV and still using a low energy collimator, we make a new simulation. We're using the low energy general purpose. But now we have 400 keV here. So let us now look at this result. So now you can see that we have penetration effects here. And with these well-recognized stars here, 6 lines, because we use a hexagonal whole. I've also shown now how you can make problems for you if you don't open up too much of your acceptance angle. So let us now say that we use not number 3, but we use a value of -30. So let us now see what's happening in these simulations. We have 400 keV photons. We have the penetration collimator 50 number 1. Select that. So what you now see is the fact that I have only allowed a maximum angle of 30 degrees, which means that I have the penetration, but it's restricted to 30 degrees acceptance angle. So be careful about when you want to include penetration that you expose the whole camera, and that is the most safely done is to use number 3, because SIMIND then calculates a proper angle for you. The SIMIND use a lot of variance reduction. You have to know about the scatter order because it's not just random emission in the phantom. The SIMIND use a variance reduction called splitted photons, which means that we start from one photon and then we split that into subphotons. The thing here is that because we use split photons in the program, we have to define the maximum scatter order. And that value depends on many things. For example, if you look at the main peak window, and that is the main purpose for your simulation, it's a waste of simulating too many scatter orders. But if you have several energy windows, if you are interested in the whole energy spectrum, you need to look so you don't simulate too few scatter orders. And the thing how it works is that you define the decay somewhere, and then this emission is splitted by a primary that will go directly to the camera, and then a scattered photons that will be simulated properly and maybe come to this point here. So now here we have the first scatter order. We split that photon into 2, one going up to the camera and one that is continued maybe to this. So for each scatter interaction point, there will be 2 photons, one primary and one scatter. And then it goes like this. Here I stop, because in this case, I have said that I only use 4 scatter orders, 1, 2, 3, and 4. And this scatter order is controlled by a switch/SC, and as a default is set to 3. Before the simulations example, I will also talk a little bit about the units of the image and the spectrum. Because we are using, I'm using a lot of variance reductions to speed up the calculations in SIMIND. There is no counts in the image. But the values are in the image and in the spectrum is more, can be regarded as probabilities. The pixel value is the probability for detection per unique activity and time, given the source distribution and the phantom camera configuration being simulated. And this you can also get from a real measurement. Suppose you measure with a gamma camera phantom with 3 sources having a total activity of 120 megabecquerel, and you measure it in a time of 40 seconds. If you now look at your image and you divide each pixel value in that image or channel in the energy spectra, if you're working with that, with a factor that is the product of 120 and 40, you get the same units as SIMIND. And these two are controlled by either the index 25 in the change with the activity. Often it's just set to 1, which is 1 megabecquerel. And you can also add a specific acquisition time with the switch AT in your command. So let us now simulate a point source in a phantom to look at the scatter order and so on. I have prepared a file with the same point source as we did before. So I now simulate this point here. And it's for a gamma camera, and we now have included scatter in the phantom. So if we go up and look at the initial data, we have a scatter order of 3. And this is a cylindrical water phantom and the point. I have also stored the spectra here. So when we want to plot this, sometimes we need to convert this to text files because they are stored in binary. So there is a program called BIS, which I need to use because I will now use the GNU plot as the way of plotting spectra. So I make a conversion for that and now go over to this window. So now I can plot point.prm, which is the result from the BIS program with lines. So now I have a spectra here with the main peak here and a Compton scatter distribution. And it looks fine, but this is not correct. Why? Because we have only allowed 3 scatter orders. If you're only interested in this area for the image, you will see from the result file that the number of events that goes into the energy window that has been scattered 3 times are very low, 1.8%. So this information in the result file give you a hint of how many scatter orders do I need. So we have to redo the simulation and change the scatter order, for example, to 10. So now we allow 10 scatter orders. This will take a little bit longer time because it's more splitting and more calculations. So that's why you have to figure out if it's worth it or if you only need a certain number of scatter orders. So now this is finished. I need to do this, but what I will do now is that I will store this new file to a new name, point1. And then I go over to GNU plot and I will replot, which means overplot with the new data here. So now you can see that the shape of the energy spectra have changed because now we have added the possibility for more orders, that more scatter orders means more energy depositions in the phantom, which means that the photons that reach in the camera will be mostly low energy photons, and that appears here. You see here it converts to the same shape here, So the first run is okay for this energy range, but not okay for if you want to look at the large energy range here. Finally, I would like to show you how you add noise to the images, because these are what you say probabilities. It doesn't follow the ordinary Poisson distributed noise that you find in your real measurements. So the procedure is that you can simulate with the SIMIND a quite good average image by selecting a lot of histories and doing a long run to get very low noise images, but they don't represent the noise in a real situation. So if you want to mimic that, you can scale these images to the proper activity and the acquisition time, and then add noise to it. So you can use a program called BIM, which is in the distribution. So I will now simulate a scenario where I put in the whole body simulation, assuming an activity of 600 megabecquerel and an acquisition time of 120. And I will simulate this for a long run, which means that I add this scaling possibility switch NN to 100. And then I will use this BIM file and add noise to it. You give your simulation here, which I call VB1, which is your simulated Zubal phantom. You give an output name, and in this particular case, I want to scale it to an integer image. You have to give the matrix size for the X and Y dimension. In my example here, I have this large whole body matrix 124 times 384. You add a switch here, NO stands for noise. This means that the input is in real format or floating format, and the output should be in integer format here. So now let us see what the simulation have given us. I have already simulated this because it takes some time. So now I have two cases, one with interaction and scatter in the phantom and one without. And I will add noise to both of them. So I go down here, and the first one is called MDP VB1, and that is without interactions, and I add noise with the BIM program. And then I change to VB2, which is the version with interaction and scatter, and I do the same. So now I have two files here called VB1._int and EB that has noise, and it's also integer format. So now I go in with the image J import, and I select, first I select this file here, VB1.int, and I have to give this unsigned integer here because it's now 2-byte integers. So now I have the file here, which has been added noise to. And now I go in and open the one that is the underlying raw data for this file, that is called VB1 BIM. I have to change now to 32 because this is no noise. So here you can see perhaps that this is much smoother, and this has been added noise, but this is the air image. We can see that because we see the spine very clearly over the whole range. There is no attenuation. So now I put this here aside, and I will put the other one here aside. So now I will open the other two files, import raw, I will open input VB2 int. I change this to 16-bit and open that. And we put that here. And the final one we open, which is the original non-Poisson noise image for the attenuation and scatter, and that is called VB2 BIM. And we change it back to 32-bit real because so here we now have the 4 simulations. We have the original, and we have the one with the Poisson distributed noise on. We have the original here for the attenuation and scatter, and the Poisson distributed noise. And perhaps you can see that this is a little bit more noisy because there is less counts. And it's very important that you find the correct level, because the algorithm for adding Poisson look at the pixel value. So that is regarded as the average, and then there is added noise to it accord. You can add noise in the actual simulation, but this is to prefer, because you can reuse this image here, this one here, and this one here, and make noise realizations using the same average. By that, I would like to conclude this webinar, and I hope that the things that I have gone through will be useful for you in your project. Good luck with them, and thank you. Bye-bye.